Welcome to our first unit of AP Chemistry. This will review many concepts we learned last year in chemistry, but make sure you actually know them at the AP level. Some of this will be review for you. You will likely get it the first shot. Some of which, though, we will mention but mostly skip over as you're expected to still remember them from last year. Please keep in mind that if you are stuck on any of these, it's definitely worth time actually reviewing your book or even coming to me during tutoring. These are the objectives we have for the first unit. They're actually quite high level if you start reading them, mainly because they're actually AP objectives. They take the same information you learned last year, somewhat, and require you to learn that at a much deeper level. Hopefully by the end of this unit you can achieve all these. Many of them, though, will likely be more explored and mastered throughout the year. But our hope is that you get most of them in this unit. So for our first section, we're actually examining objective 1.1, which is that students can use atomic molecular theory to explain that the element mass ratio in any pure compound is always identical. So let's start with chemistry. Chemistry is a study of the properties and behavior of matter, which is anything that has mass and volume. Chemistry also provides understanding into atoms, which are the building block of matter. So pretty much everything we study, well, for the rest of the year, will involve matter. We do talk about energy for a few things. Chemistry definitely studies energy a lot more, but all of that comes back down to matter. Matter can actually occur in three main states. You can think of them as forms: solids, liquids, and gases. Solids have definite shapes and definite volumes, meaning they have a predetermined amount amount of space they will take up, and they also have a predetermined shape. Liquids have indefinite shape; their shape can change, but their volume will not change. Gases really don't have anything said about them. There is a fourth state called aqueous. It's kind of like if you dissolve salt in water, salt is in the aqueous state. It's not really solid because you kind of broke it up, but it's not really liquid because it's in water. We will talk about that more in solutions, but it really will help you to actually keep in mind what aqueous actually means. Scientists sort matter not only into the three states, but into one of four classifications of matter, meaning anything you look at is one of these four things. It is either a pure element, it is a compound, it is a homogeneous mixture, or it is a heterogeneous mixture. Most things you see are going to be some kind of mixture, but we're still going to talk about the other two. To begin with, elements are substances that cannot be decomposed into simpler substances while retaining their original chemical identity. You can break elements down actually even farther, despite what you may have learned last year. However, you get into what are called quarks, and though if you break down, for example, a carbon atom, you don't have carbon quarks, you just have quarks. We likely will not talk about this much later, but feel free to research it on your own. Each sample of an element, however, is composed of only one kind of atom. If there's multiple atoms, it's not an element. There are currently about 118 known elements. We have a few that we're pretty sure they exist, but we haven't quite labeled them or made them stable enough yet. And the average mass of any large number of atoms of any given element is always the same for that given element. Later on we'll talk about atomic masses, but each element has its own unique atomic mass. So again, hopefully this is all mostly reviewed. Compounds are substances that are composed of two or more elements that cannot be physically separated into their individual elements. A very common example would be H2O. I'm sorry about that. Generally for H2O, this means that we have one oxygen atom and two hydrogen atoms. Now, when I say physically combined, that means, for example, if I stir up a bottle of water or a cup of water, this does not suddenly break into hydrogens and oxygens. It just stirs it around, and they all stay together. Compounds will pretty much always be represented by an actual chemical formula. Elements do too, and actually that H is an element and that O is an element, but compounds normally are multiple types of elements in one substance. Water, for example, as I mentioned, is a compound that is, regardless of its source, comprised of actually 11% hydrogen and 89% oxygen by mass, both of which are elements. Now, this actually goes back to our objective. And anytime you find water, since you're going to have one of each, these hydrogen atoms account for 11% of the mass. And this oxygen atom always counts for 89% of the mass. We talked about the average atomic mass of an element always being the same, which is why these will always be 11% and 89%. And this kind of goes back to our objective again. But as a reminder, this is just 2 atoms of hydrogen and 1 atom of oxygen, which we do commonly call H2O. Elements are compounds, and compounds are both considered pure substances, which is a substance that has distinct properties and a composition that does not vary from sample to sample. Meaning, if I find a hydrogen atom here and a hydrogen atom here, they're the same thing. It's the same hydrogen atom. Any properties of this atom are going to be shared by this atom. Just like if I find samples of water, it's all going to be the same water. Now, in tap water, for example, you may have things mixed in with it, but the actual water in it is the same thing. Mixtures, however, are different. So a mixture is actually basically a mix of pure substances and compounds. A homogeneous mixture is when we mix pure elements, which is kind of our summary for elements and compounds, in a uniform manner, meaning any sample from this mixture will have the exact same chemical composition. So let's pretend that with my wonderful artistic talents, that I have a cup of some liquid. Okay. If I were to take a sample from here and a sample from here, and I were to kind of look at them on a microscope, I would see the exact same thing in them. I really tried to put the dots in the same way, but that did not happen. You will see the same composition. This is kind of like if you think of vanilla ice cream. It always will taste vanilla in every part of the vanilla, unless they didn't make it well. But every bite should taste the same. Commonly, I also use creamy peanut butter as an example. Every bite of the creamy peanut butter tastes the same. And if it doesn't, then take your creamy peanut butter back to the store, because that's kind of sketchy. So another common example, though, is air, which is a mixture of actually nitrogen, oxygen, and, well, a few other gases. But you never really are walking around and suddenly are short of oxygen. You don't start breathing and all of a sudden start suffocating because you can't get the right minerals or elements that you need. Sometimes we call homogeneous mixture solutions, but that is definitely going to be talked about in a later unit. A heterogeneous mixture is a mixture of pure elements, pure substances in a non-uniform manner. By the way, there are a few typos on this video as you've seen before. I will edit this out for next year, but these are how your notes are printed. So I'm going to keep them so far. That way you actually can follow along with the note. I will try and change this for future units. Anyways, this is mixed in a non-uniform manner, meaning 2 samples of this mixture may have different chemical compositions. This would be like, we'll say, chocolate chip ice cream. So you've got some kind of bowl of chocolate chip ice cream. It's supposed to be a bowl. Probably should make it white. So we've got a bowl of chocolate chip ice cream. You got a little chocolate chips in it. I know, I'm a wonderful artist. I should have taught art. So if I were to actually take a sample from here and blow it up, and a sample from right there and blow it up. For this one, if I circled correctly, sample would look like this. Okay, you got chocolate chips somewhere. But I circled intentionally over there because I didn't have any black dots over there. So sometimes you may be biting chocolate chip ice cream and you get a ton of chocolate chips. But you also may get bites where there's none. The fact that those are different means it's a heterogeneous mixture. So while we've talked about classifications, now we got to actually mention the atomic theory, which is the second part of our objective. In the early 1800s, a scientist named John Dalton proposed his theory on how atoms are structured, and we often call it Dalton's atomic theory. It was composed of actually four main postulates, or four main points, if you will. First off, every element is composed of extremely small particles called atoms. He really didn't go too much farther, and while that's true, he later implies that they're actually indivisible. He's actually wrong on that. We'll learn later that atoms have electrons, protons, and neutrons. It is important to know that he was wrong on this part. We'll focus on that a little bit later when we can actually refute it. Secondly, he says that all atoms of a given element are identical, but the atoms of one element are different from the atoms of all other elements. In summary, the first part he's wrong, but the second part he's right. Go John Dalton. He is wrong because we have what are called isotopes. I will write this, though we will be addressing this in a few units. But hopefully you remember this term. This is where they have the same amount of protons, but different amount of neutrons. It's the same element, but they're not identical. So John Dalton tried, but he was wrong. And like point 1, or postulate 1, it is important to know that he is wrong, but we will also discuss this more later. Thirdly, though, he says that atoms of one element cannot be changed into atoms of a different element by chemical reactions. In summary, atoms are neither created nor destroyed. This means that if you combine hydrogen and oxygen atoms, you're not getting a third new atom called water. Water is simply a compound that forms or is made up of hydrogen and oxygen. So they cannot change into different types of atoms. Fourth, he finally defines compounds, and he says that compounds are formed when atoms of more than one element combine. And then he actually goes farther and says a given compound always will have the same relative number and kind of atoms. And he's right in this. Water is what is formed when hydrogen and oxygen combine, and water will always have two hydrogens and one oxygen. So he's definitely right on this, and actually many of our laws that we use regarding all these come from this postulate. So while parts of this theory ultimately proved to be incorrect, mainly his first two, it still shed light on many aspects of chemistry that are still important and true today that we're about to talk about. First off, is we actually get the law of constant composition from postulate 4. This states that in a given compound, the relative numbers and kinds of atoms are constant, which sounds a lot like what he just said. This explains, however, why, as mentioned before, water is always 11% hydrogen and 89% oxygen by mass. If these are false for a specific compound, it is simply not water. There's no give and take on this. It's either 11 and 89% or not water. Secondly, we can get the law of multiple proportions from this theory. This states that if two hypothetical elements A and B combine to form more than one compound, the masses of A or B that can combine with a given mass of A are the ratio of small whole numbers. So, in a little bit more English, or chemistry, this explains why we can find H2O and H2O2. And actually, you could probably even find H2O3, but not H2O 1.5. We need whole numbers. and they're going to be some kind of multiple of either 1 or 2. And not much bigger. You'll find whole numbers. They'll all be kind of similarly related to each other. Well, in our next section, we're going to talk about empirical formulas. This is a concept that if you are coming from honors chemistry, you covered. If you're coming from general chemistry, you did not cover. You are still responsible for knowing the information. But specifically, we have 2 objectives. First off is number 1.2. Students can use mass data to quantitatively identify or infer the compositions of pure substances and mixtures. And 1.3, students can use calculations of mass data to determine the identity or purity of a substance. Mainly this will be coming down to empirical formulas and identifying from there, but this is definitely an objective we'll use throughout the year. So, many elements appear in nature by themselves. Some, however, appear in groups of elements. Most notably, elements that naturally appear in pairs of the same element are referred to as the diatomic molecules. The most notable ones being hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. And the symbols of these elements spell the, nonsensical word Hofsprinkle. Now that means that anytime they appear in an equation, they come in pairs. So it is not hydrogen and oxygen producing water. It is H2 plus O2 producing water. Now, yes, you have to balance that, but we'll deal with that later. Chemical formulas, like H2O, are commonly used to indicate the actual numbers and types of atoms in a substance. For example, we have 2 hydrogen and 1 oxygen. Those used to indicate the composition of compounds are called molecular formulas. Chemical formulas, however, that only give the relative number of atoms are called empirical formulas. So basically the lowest amount we'll talk about is an empirical, and basically whichever one you're using is the molecular. It's a lot less complicated than it sounds. In an empirical formula, subscripts are always the smallest possible whole number ratio. For example, while the molecular formula of hydrogen peroxide is H2O2, telling us that we have a 2:2 ratio of hydrogen to oxygen, we can really reduce that down to a 1:1 ratio, or just HO. This is our empirical formula. This is our molecular formula. And that's the difference. So let's do a little practice. Let's write the empirical formulas for A, glucose, which is a substance also known as either blood sugar or dextrose, which has a molecular formula of C6H12O6. Well, hopefully you notice that that really comes down to a ratio of 6 to 12 to 6, which if we divide all those by 6, gets us a 1 to 2 to 1 ratio, which would be C1 H2 O1, which is C H2O. You actually can leave it as this if you'd like, but we normally don't write the ones. Nitrous oxide, which is a substance used as an anesthetic, and commonly we just call it laughing gas, which has a molecular formula of N2O. Well, we've got a ratio of 2 to 1, and can't really reduce that. If we try to anymore, we'd get 1 to 1/2, but we need whole number ratios, not fractions. So our empirical formula is also our molecular formula, N2O. And there you go. So empirical formulas are often related to the percent composition, or sometimes the mass percent, of a compound, which is the percentage by mass of the elements in a given compound. As mentioned before, the mass percent of water is 11% hydrogen and 89% oxygen. That means that in every 100 grams of water, that word percent, well, that sign percent, means per cent, cent being the prefix for 100, so per 100 grams of water, we have 11 grams of hydrogen and 89 grams of oxygen. So that is referred to, this is referred to as the percent composition of water. So if two molecules of the same element happen to have the identical percent composition, they're also going to have the same empirical formula. If that happens, it makes our job a lot easier. But normally, that's not going to happen. So let's calculate the percentage of carbon, hydrogen, and oxygen by mass in, well, this scary looking compound. Now, when we deal with actual percentages, ultimately we're trying to figure out how much of the total mass of this comes from carbon. So first, let's find our total. So our total in this case is going to be 12 times the mass of carbon plus 22 times the mass of water plus 11 times the mass of oxygen. Hopefully you actually remember how to do atomic masses. If not, better learn pretty quickly. Either way though, this comes down to 342.34. That says that in 1 mole of this, hope you remember that word, 1 mole of this will have a mass of this. So our percent carbon would then be that 12 times 12.01 over 342.34, which is equal to 42%. By the same logic, our percent hydrogen, I'm going to let you actually do the work, is 7%, and our percent oxygen is about 51%. Now I did round these just because it was a little bit easier to write. You don't normally have to. Now, commonly I actually keep this to be like 42 point something with 1 decimal point. It's up to you. But the fact that we have 42%, 7, and 51 would be our final answer. Alright, in addition, since pure compounds have a specific mass percent of each element, experimental measurements of percent compositions can actually be used to verify the purity of a compound. That goes back to our objective. So if we're given certain percentages of a compound, we can determine whether it actually is the compound we're looking for or not. That's kind of where empirical formulas are mainly used. So that means we need to know how to determine an empirical formula. This procedure can be used to do that. So basically it's percent to grams, grams to moles, moles to mole ratio to formula. Well, let's see what that means. Percent. That means determine the percent composition of the substance. Make sure you actually sum the percentages of the same element. So for example, in NH4, NO3, you really need to think of this as N2H4O3. A lot of students tend to forget that there are 2 nitrogen. They'll do the percent of both, but they'll treat them as different elements. Sometimes you are also given the percent composition, and in that case, go right to number 2, which is grams. We are assuming that we are have a 100 gram sample. Now, we may not. I get that. It's fine, but we're still going to assume that anyways. So our percentages are now treated as masses. This is like when I said we had 11% of hydrogen in water, and I said, well, that means we're going to have about 11 grams of it if we had a 100 gram sample. So really just change your percent signs to gram signs. Thirdly, moles. Convert those amount of grams that we have into moles of that element. And then round that number, I normally choose about 2 decimal places. Because next we do our mole ratio. We divide all the moles that we just obtained in this section by the smallest number of moles. Commonly, you'll end up with about the same numbers, or at least 2 of the elements. If there's 3, we'll actually have the same number for the mole ratio. But at least one element should always result in 1.00 because you're going to have the smallest divided by itself. So if I've got, I don't know, 3, somehow I got 3 moles, and 1.5. The smallest is 1.5, so my mole ratios will be 2, 2, and 1. So there you go. Finally, and the most annoying part, is we need to find the lowest whole number ratio of those moles. So when we had 2, 2, and 1, those are all whole numbers. That's great. That's fine. That actually works for us. But what if somehow we had 1, 1, and 0.5? Which, yes, is the same thing, just cut in half. We can't really round this number up to a 1 and say, well, 5's number to round up, because now we have a ratio of 1 to 1 to 1, when it actually should be 2 to 2 to 1. So we actually have to multiply all the numbers by integers, namely the same integer, until they're all whole numbers. So if we have 1, 1, 0.5, we need a number that I can multiply all these by until all of them have a 0, 1, or 9 after the decimal. Now, technically, you can argue to have an 8 after it. Sure, whatever. You really want to do that in the AP test? Have fun. They're probably not going to care, and if you show your work, they're probably going to trust you. But generally, I'm used to 0, 1, or 9. So you probably noticed, but if we multiply these by 2, we'd get 2.0, 2.0, and 1.0. We got 0, we got 0, we got 0. Huzzah! We can actually now round those to whatever number they round to. So 2, 2, and 1. If after multiplying, let's say we had the numbers 1.3, 1.3, and 1. So if we multiply all those by 3, we'll get a 3.9, 3.9, and 3. So we got a 9, and that's a whole number, so it's just 0. But that means these will turn into a 4, 4, and 3, not a 3, 3, and 3. Once they end in a 0, 1, or a 9, I'm not sure what that was, 0, 1, or a 9, you round to whatever number they currently round to. So the 9s will round up, and the 0 and 1s will round down, technically. So those numbers, once they're 0, 1, or 9, become your subscripts. And there you go. That's an empirical formula. Let's try this though. So I'm going to show you, I'll show you the whole thing. So we have 40.92% of carbon, 4.58% of hydrogen, and 54.50% oxygen. So that's our percent. We now need to go into grams. So I'm going to change these to grams. Whoa. Now we go grams to moles. So times it by 1 mole over 12.01, 1 mole over 1.01, and 1 mole 16.0. This gets us about 3.5 moles. It's a little bit off, but I'm just going to round. This gets us about about 4.5 moles. And this gets us about, I believe, 3.5. About 3.5 moles. Okay. So the smallest in this case is a 3.5. So we divide all of them by 3.5 and we get 1 mole. I will come back to that because I do not know that answer in my head. This will also get a 1 mole, and our third will get us about 1.3 mole. Well, now we've got a 1 to 1.3 to 1 mole, and we need to get this into whole numbers. Timesing these by 2 will get us a 2, 2.6, and a 2. That's not good enough. We need to times these by 3. So that'll get us into a 3, 3.9, and 3. Since those are our actual subscripts, we can round those up to 3, 4, and 3, since they all end in 0, 1, or 9, which means our empirical formula is C3H4 0.03. And that's an empirical formula. Now that we've talked about determining empirical formulas, our next step is actually to determine molecular formulas. These are basically the type of formulas that we will normally use on a daily basis. Molecular formulas can be empirical formulas at their heart, but normally when we say empirical, we think of just the ratio, while molecular, we tend to think of whichever one we're using. Now, since the empirical formula is the ratio of atoms within a compound, and that ratio has to stay the same, the molecular formula is just going to be some whole number multiple of the empirical formula's subscripts. So if, for example, we have a 1 to 2 relationship as our empirical formula, we may have a 2 to 4 as our molecular, or a 3 to 6 as our molecular. Still can be simplified down to that 1 to 2 relationship. So to determine the molecular formula, at least assuming we have the empirical formula, all you need to do is actually take the molecular formula's molar mass and divide it by the empirical formula's molar mass. That will actually get you the whole number that you can multiply your subscripts by. So, well, kind of a boring example. Let's assume that our molecular formula molar mass was 30, okay? And our empirical, let's assume it's 15. This will come down to a whole number of 2. Now, let's pretend that our empirical formula had A1B2. Then our molecular formula would be A2B4. We would multiply those subscripts by 2, which is our whole number ratio of the molecular formula molar mass over our empirical formula molar mass. So, as an example, mesitylene, which is a hydrocarbon found in crude oil, has an empirical formula of C3H4 and an experimentally determined molecular weight of 121 AMU. What is its molecular formula? Well, first thing we need is actually our empirical formula molar mass. Fortunately, we have our empirical formula, which is C3H4. Well, our molar mass will be 3 times 12.01 plus 4 times 1.01, which I'm going to round to about 40. Our ratio of molecular over empirical then will be 121 over 40, which gets us about 3.1, and I'm going to round that down to 3. By the way, this should always come down to some whole number. So if it came down to like 2.4, we have an issue. That means that you likely determined your empirical formula incorrectly. A 2.9, sure, we can round that to a 3. 3.1, sure. You probably could even argue for a 2.8 or a 3.2, but besides that, gotta recheck your work. Anyways, since our whole number is a 3, that means our final molecular formula will be C of 3 times 3 and H of 4 times 3, which is C9, H12. Now this next section, we're talking about molar mass, mass in particles, and this will begin talking about us being able to interconvert between particles, moles, mass, and eventually we'll talk about volume too. Much of this I'm expecting you already know from first year chemistry. I'm not covering much in this. It's your responsibility to know that that came from your summer work. But it is important to know that atoms have very small masses, and so small that it's really cumbersome to write their mass in actual grams. So instead we use what's called the atomic mass unit, where 1 AMU is equal to, well, that many grams. While you don't quite need to memorize that number, it is important to know that the atomic mass unit represents the mass of one atom. Now, most of our calculations will be using grams, but as we saw actually even in our previous example, you can think of AMU as grams as interchangeable. So that's the biggest thing I need you to know. In addition, because of how it's defined, the mass of an individual atom or molecule in AMU is numerically equivalent to the molar mass of that substance in grams. So that's actually why we can assume that AMU and grams are interchangeable, because we're either talking about molecules or moles, but the number is not going to change. So in addition, and largely thanks to Avogadro's number, which again, I'm assuming you know, for any sample of a pure substance, there is a specific numerical relationship between the molar mass of the substance, the mass of the sample, and the number of particles. Basically meaning you should be able to go from moles to grams to atoms, and vice versa, and are actually not in that order. So grams to moles to atoms, going anywhere in between those. Now, in this next section, we're starting to talk about chemical equations. And, well, those are your objectives. Chemical reactions are often represented by chemical equations, such as the one below. Especially when balanced, these are extremely useful, and you will see these all throughout AP Chemistry. Let's check what equations can look like. The following diagram represents a chemical reaction in which the red spheres are oxygen atoms and the blue spheres are nitrogen atoms. Write the chemical formulas for the reactants and products. Well, our reactants, we've got little things of two red spheres. So that's going to be an O2. And then we've got some red and blue, which are in O. As our products, looks like it's going to be in O2. Balanced equation for that reaction, I'm actually going to write that up here. O2 plus NO, producing NO2. Well, I'm going to assume we're probably going to need a 2 here, to put a 2 here, and actually balances. So 1, 2, 2. Well, is the diagram consistent with the law of conservation of mass? What that means is, do we have the same amount of red spheres on the left as we do on the right? I'm going to let you count them, but it turns out you actually do. You'll have 16 red spheres on the right, 16 on the left, 8 blue spheres on the right, blue, and 8 on the right. So you end up working out, so yes, it's consistent, which all balanced equations should be. The most common types of chemical reactions are combination, which we used to know as synthesis, decomposition, combustion, single replacement, and double replacement. There are also acid-base reactions and redox reactions, both of which come down to double replacement, but we'll talk about those later. With most of these reactions, you will, by the way, be expected to not only classify, but also predict the products. So if I give you two things that react, you should be able to tell me what they'll produce. Combination reactions, which again we knew as synthesis, occur when two or more substances react to form one product. For example, magnesium metal burning brightly is this equation. But again, you should be able to tell that if magnesium and oxygen combined, then we're going to have magnesium oxide. So please make sure you know how to do those. Decompositions occur when one substance reacts and produces two or more substances, kind of breaks apart. That's an example of calcium carbonate. We got calcium oxide and carbon dioxide, which by the way is common with most carbonate decompositions. Calcium oxide, no, you got to have the calcium in there, but you'll commonly see carbon dioxide. Combustion reactions occur when we combust a hydrocarbon, which is anything involving C's, H's, and sometimes O's. For example, this one has a C, has an H. There's no O, but that's fine. Combusting in air means adding O2, and it should always produce carbon dioxide and water. If there's not enough oxygen, which it would tell you, you'll produce carbon monoxide, which is why smoke really isn't all that good for you. Sometimes you're getting carbon monoxide in there as well. Luckily, not too often, but still. Don't go breathing smoke. Single replacement reactions occur when an ion in solution is displaced through the oxidation of an element. Or in a little bit more English terms, in this reaction the magnesium is replacing the hydrogen. So now the hydrogen's off by itself and magnesium's got magnesium chloride. The These type of reactions will occur due to an activity series, which we'll talk about more in Unit 4. Maybe 4. Actually, no, Unit 5. I know you don't really care, but Unit 5. We'll talk about that later. But basically, if magnesium will swap out hydrogen, then that means that the reverse reaction will not happen because magnesium is more active. Anyways, we'll talk about that later. Double replacement reactions are reactions in which cations and anions appear to kind of change partners. This is occasionally called exchange reactions, even less commonly metathesis. Sometimes it's double displacement. But generally you can tell this because you've got two ionic compounds, two binary ionic compounds specifically. And basically the cations, that was just straight up ugly. Let's try that again. The cations, there we go, will swap places. So now instead of silver nitrate, we have silver chloride. Instead of potassium chloride, we have potassium nitrate. Technically, we only know this occurs if we produce some kind of a solid. Normally, we call it a precipitation reaction because that solid's called a precipitant. But double replacement, when it comes down to it, is just two things are replacing each other. As I mentioned, though, we do need these only officially occur if a solid is formed, which we actually need to consult solubility rules. We'll actually get those in a few slides, but for right now, don't worry about them. All right, welcome to net ionic equations. Yay. They're actually kind of fun, but to be honest, most people need more practice with them, so you may not like them at first. Most equations are written as molecular equations, which basically show every stinking thing that happens in the equation. While that's cute and great, we honestly don't normally care about it. For example, this reaction. You may at first think, oh, lead nitrate and potassium iodide. That's forming lead iodide and potassium nitrate. That's a very helpful equation. Well, if so, you're wrong, because that tells you way too much information. You really don't care that much. This would be like if someone asked you what happened at the football game, and they tell you how many people were in the audience. They tell you what snacks they bought. They tell you what scores they played. They tell you every single player who played every single play and on the bench. It's just too much information. Honestly, all I really care about is did our team win or lose? And sometimes I care about by how many did they win or lose. That's really about all I care about. So, an equation that shows every dissociated ion is called a complete ionic equation. This is officially like saying every single player that played in the football team, or in the football game. Again, while they're awesome, the players are great, I honestly don't normally care. Probably just because I really can't keep track of it, and personally I don't know much about sports. If you do, then that's great and all. But I don't normally care how many guys played every single down. But this is our first step in determining the net ionic equation. You hopefully noticed, though, we didn't split up this compound. You only will split up aqueous. Technically, they're called electrolytes. We'll get that later. But for now, just split up aqueous compounds. Keep together solids, liquids, and gases. Which is actually what we're talking about on this slide. Well, that's awkward. So, it was a precipitate. Sometimes we'll also call that precipitant. Personally, I do not know the difference. So if you figure out the difference between precipitate and precipitant, let me know. But I'm assuming since I don't know, you don't need to care. But again, we'll only dissociate strong electrolytes, which right now you can treat most aqueous compounds as that, and keep together solids, liquids, and gases, regardless of what side they're on. So if they're reacting as a solid, keep it. Products as a solid, keep it. All right. So ions that appear in identical forms on both sides of the equation of a complete ionic equation are called spectator ions. They really play no direct role in the reaction. These are like the football players who they came in, the coach brought them in, they're the receiver, for example, who runs out and he doesn't have the ball thrown to him. It's great, but he really didn't do a whole lot in that play. For example, potassium and nitrate were both spectator ions. They were aqueous on both sides. It really didn't do anything. So if we were to actually take those out of our previous equation, that's our net ionic equation. This would be like, instead of telling me in a football play, I really don't know why I keep doing football plays, but this would be like, instead of telling me, I'd on this down, all these guys went out, this guy went here, this guy went here, this guy went here, you're really just telling me the quarterback threw the ball to this guy, he caught it, he got tackled. I don't really need to know much more information. So it's just telling you really what happened. So for our original equation, while originally we thought, yay, this is cute and useful, it's not. All I really care about knowing is that this and this combined to form this. I don't care about potassium. I don't care about nitrate. In the end, they're just floating around in solution. I still don't care about them. This is our net ionic equation. You'll notice, though, they are balanced. We have 2 iodine, 2 iodine, 1 lead, and we've got a total of a 0 net charge on here and a 0 net charge over here. You do need to balance these both by atoms and charges. Make sure they're actually balanced. Okay, I gotta stop doing this whole thing about telling you before the slide, but if they're done properly, they should be balanced. There you go. All right. The solubility guidelines on page 121 of your book can be very useful for constructing net ionic equations. Occasionally on your AP test, you'll be given tables that you can use, but you are expected to memorize a few of these rules. And, well, here they are. These are the only rules that you're expected to memorize, which is that compounds containing alkali metals, so sodium, potassium, lithium, technically the ions, all the way down to francium, nitrate, and ammonium are always soluble. There are other compounds that are always soluble. I'm pretty sure acetate's always soluble. There's something else that I don't remember. But all you need to care about are these. So, meaning if you're ever asked on the AP exam to do solubility, they will give you enough information where with whatever they give and with this, you can solve the problem. Personally, I recommend trying to memorize more. Take the table on page 121, try to memorize it. This should be the minimum. In fact, you should already know this, but that's another story. The more you memorize, the easier it is for you. So let's do a net ionic equation for the precipitation. Hey, look, one of them is going to precipitate. That occurs when aqueous solutions of calcium chloride and sodium carbonate are mixed. All right. Calcium chloride plus sodium carbonate are mixing. Hopefully you notice this is a double replacement reaction. If you see the word precipitation, generally you're going to have a double replacement. That means we've got calcium carbonate, I don't know what state it's going to be, plus 2 sodium chloride. Mr. Booth, why did you press 2? Because I had to balance the thing. If you got 2 sodium, 2 chlorine, put a 2 there, yay, it's balanced. By our solubility rules, we know that all alkali metals, nitrates, and ammoniums are always soluble. Nitrate and ammonium do not help us. But we know right here that, hey, look, alkali metal. That means aqueous. We have a precipitation reaction, which means something has to precipitate out, which means that has to be a solid. After a little bit of work, our net ionic equation, therefore, will be calcium 2 plus CO3 2 minus produces calcium carbonate. Personally, I saw there's 2 sodiums, 2 chlorine, 2 chlorine. I didn't want to write the complete ionic equation out. You can if you want. I normally don't want to. There you go, though. Welcome to stoichiometry. Yay. In chemical equations, the coefficients represent the relative number of molecules in a reaction. Not technically moles, definitely not grams, but we normally just treat it like moles. So that does not mean relative numbers of grams. Seriously, just stop thinking that. Like, just stop. So when we react two or more reactants together, one of them, or more if it's a tie, will run out first. When that runs out, the reaction cannot go farther. You cannot make s'mores if you run out of graham crackers. You cannot make sandwiches if you run out of bread. Unless you're doing lettuce wraps, or you get the point. The reactant that runs out first in a reaction, which ultimately is going to produce the least amount of product because it's going to run out first, we call that the limiting reactants. I'm guessing you can guess why, but in case not, it's because it limits the reaction, and it's a reactant. Yay. So the amount in grams of whatever product we're desiring, again, in grams, that the limiting reactant can produce is called the theoretical yield. Meaning, if you're ever asked for the theoretical yield, you first need to find the limiting reactant. Try not to forget that. But the amount that is experimentally obtained, meaning we actually run the experiment, we perform it, whatever we actually get, that is called our actual yield. This is typically less than the theoretical yield simply because, well, we're human. We're not great at doing things perfect. So if you ever happen to have a job and you know the theoretical yield, tell them that whatever you obtained is a little bit less, otherwise they're going to think you're lying, and well, you probably will be. So make sure you remember, actual is less than theoretical yield. That's supposed to be a less than sign. I'm just going to move on. So the percent comparison of actual yield over theoretical yield is, well, the percent yield. This is exactly what you do on tests. For example, let's say on a test it's worth 60 points. You get 45 of them right. And you're thinking, oh, what grade is this? Well, 45 over 60 ends up getting a 0.75. Times that by 100%, you get a 75% grade. That's literally exactly what we're getting. Theoretically, you should have gotten 60. You actually got 45, so percent-wise is 75%. So adipic acid, which is that, is commonly used to produce nylon. And it's made by, well, that reaction. Now let's assume you carry out this reaction with 25.0 grams of cyclohexane, and cyclohexanes are limited reactant, which makes our job a lot easier. What's our theoretical yield? Normally, if you did not know your limiting reactant, all you got to do is figure out, like you'll be given amounts of two different substances, convert them both to whatever compound you're trying to go to, and see which one produces the least. In this case, we know that cyclohexane is going to produce the least, so that saves us a lot of time. So all we got to do is take 25.0 grams of our cyclohexane. We need to go to moles of cyclohexane, which would be about 1 over 84.0. That's our molar mass of cyclohexane. We've got a 2:2 ratio of cyclohexane and adipic acid. And then finally, we want to go to grams of adipic acid, which will then be about 146.0. I already calculated this out, as you probably figured. Multiply that out, you get about 43.5 grams. That says that theoretically, if we react 25 grams of cyclohexane, we'll get about 43.5 grams of adipic acid, assuming we have sufficient oxygen. Now, part B down here says, if we actually obtain 33.5 grams, what's our percent yield? Well, we were shooting for 43.5 grams. That's our theoretical yield. We actually got 33.5 grams. Our percent yield then ends up getting us about 0.77, which is about 77%. Again, the biggest thing you're going to deal with is if they give you two different reactants, just take them both, figure out which produces the least. Sometimes they'll give you percent yield, but just take your percent, multiply by your theoretical, and I mean, seriously, you should know this from last year. If you don't, come talk to me. Or see some of my other videos from Unit 2. Yeah, Unit 2 should have it from General Chem. All right, so combustion analysis. Fire. A common lab technique for determining empirical formulas is to blow them up and analyze what happens. That's literally combustion analysis. You combust it and analyze. When a hydrocarbon is combusted in this way, the amount of H2O produced is determined along with the amount of CO2 is produced. Basically, you burn things and you've got a water absorber and a carbon dioxide absorber, and you track how much actually is absorbed. From there, you can figure out how many moles of C and H are produced. And then if there's anything else in the hydrocarbon, like oxygen commonly, you can figure out how many grams of C and H came from the original compound, and then whatever's left had to have been oxygen. So that's it. We're actually going to do an example using this. Steps are A, determine your mass of carbon in the original compound from your carbon dioxide. So you'll likely have grams of carbon dioxide, just convert that to grams of carbon. Do the same for hydrogen and water. If those are all you need, then just make the empirical formula off those two masses. But normally you'll have a third one. So take the mass of carbon and hydrogen, subtract it from whatever your initial mass was, and that'll give you how much, we'll say, oxygen is left. Then use those to find your empirical formula. So, isopropyl alcohol, commonly sold as rubbing alcohol, is composed of C, H, and O. Notice we have the O this time. Combustion of that many grams produces that many grams of CO2, that many grams of H2O. Determine the empirical formula. Now, hopefully you're thinking, well, wait a second. Well, actually, hopefully you're not thinking this, but you might be thinking, wait a second. We combusted about a quarter of a gram, and we got more than half a gram. We got almost a full gram of other stuff. Keep in mind you're adding oxygen to this, so don't let that freak you out too much. But let's work on carbon first. So we've got 0.561 grams of carbon dioxide. We basically need to get to moles of carbon dioxide, because then we can figure out how many moles of carbon we have, then figure out grams of carbon. If you know the percent composition of carbon dioxide, just you memorize that for sheer boredom. You can use that too, but most people don't have that memorized. So instead, multiply that 1 by about 40.01. In carbon dioxide, we have 1 mole of carbon for every 1 mole of CO2. That's what the subscript means. And then multiply that by 12.0 grams over 1, which is our molar mass of carbon. We'll get 0.153 grams of carbon. Typically, I recommend you actually label these units, but if you're stuck on stoichiometry type stuff and you're in AP Chem, pick a different class. Like, you should know how to do this. All right. So then H, we've got 0.306 grams of H2O. So our molar mass is 18.01. We have 2 moles of H in 1 mole of H2O, again, subscripts. And then our molar mass of hydrogen is 1.01. That gets us about 0.068 grams of H. All right, that's awesome. That's cool. Except, here's the thing. Those things do not add to 0.25. Because, well, we're still missing oxygen. So hopefully you wrote those numbers down somewhere. I did, so I'm actually going to erase all this. No, actually I don't think I will. I'll put them up here. So our grams of oxygen, then, is just going to be that 0.255 minus our other masses. So 0.153 and 0.068. Magical calculator powers activate. / let me look at my notes, and you get 0.068. Oh, that's awkward. Sorry, I wrote the wrong number down here. This should have been 0.343. Yeah, that's awkward. So let's just pretend that didn't happen. So we have ultimately that 0.153 grams of carbon, 0.0343 grams of hydrogen, and 0.68 grams of oxygen. Okay, now we need to get our empirical formula. Well, this part's actually not too hard. So we need to actually find our actual moles of carbon. So we had 0. Ultimately, our empirical formula, need to remind you this, percent to grams to moles to our mole ratio to our formula. Well, we don't really need percent because we already have grams. We can honestly just kind of skip from grams to moles. Normally this doesn't quite apply, but since we know all these are already in kind of ratios, we can just go straight to moles. It's going to keep the same amount of ratio. So, if you really want to though, you can divide all these numbers by 0.255 and yay, you get percents. Have fun. Anyways, so our moles of carbon will be 0.153 times 1 over 12.01, which gets us about 0.0128. Our moles of, that's carbon, moles of hydrogen will be 0.0343 times 1 over 1.01, which gets us 0.0340. Really didn't change much. That's hydrogen. And oxygen will be 0.068 divided by the molar mass of oxygen, which gets us 0.0043. Alright, empirical formula wise says actually divide all those by the smallest number. So we're going to divide all those by 0.0043. And what you'll get, your carbon is about 3.0, hydrogen is about 7.9, oxygen is 1.0. All these are close enough to actually round up. So we can actually just kind of assume that's an 8. And our empirical formula is C3H8O1. Long, painful process that really wasn't all that bad. Feel free to rewatch this, well, as many times as you wish, but that's how you do combustion analysis. Welcome to our last section, gravimetric analysis. We're actually not doing any examples on this. I'm really just telling you what it is. We actually did a lab in class on this, so you should have an idea what it is. It's just a lab technique that you should be able to know how to do. Basically, many times you're interested in a certain product through precipitation, as in you mix two things together and they form precipitate. Normally this is to measure the original some property of water. For example, our lab was measuring the hardness of water, as in how much random other stuff is in the water. And we did that by precipitating out calcium carbonate, I think. Yeah, so we tracked that and used that to determine how hard the water was. To do this, we use gravimetric analysis. So, in gravimetric analysis, a substance is added to a solution that reacts specifically with a dissolved analyte, which is whatever you're trying to analyze, to form a solid. We added, I think, sodium carbonate to calcium chloride solution. I think this is representing the water, but basically that gave us calcium carbonate in our lab. So the mass of that solid, we can then actually pull some stoichiometry and figure out what was the initial concentration of, I think it was that one. Anyways, one of them we actually knew. Oh, yep, the calcium chloride we knew. And then you can figure out what the initial concentration was. In this case, we can figure out the hardness of our water. Again, just using a bit of stoichiometry, grams to moles, etc., gravimetric analysis. So it can be formed many different ways, but it commonly follows these steps. First, you dissolve the analyte if it's not already in solution. Ours, we actually had to dissolve sodium carbonate. Dissolve one of them. So then you add the reagent to that solution and you allow the precipitate to form. That's why you need it in solution. So you let this precipitate start forming. Then you carefully separate the solution to obtain the precipitate. We filtered it out, and actually we're supposed to then put it in an oven and dry off the water, so that as best we could we had just the actual precipitate. So, which is actually step 4. We generally then heat it to remove the moisture. Sometimes this also stabilizes the precipitate. It may not be very stable in the solution form. It kind of keeps redissolving. So when we get rid of the water, there's nothing for it to do. We then weigh it, perform stoichiometry, and you can find your initial concentration. So that's gravimetric analysis. Again, in our lab, we took two solutions, added them together, measured how much solid was formed, and performed calculations on it. That was our first unit of AP Chem. Congratulations. Hopefully most of this has been a review. If you're learning it for the first time, don't tell me, just watch the video again. If you're one of the 2 people who are seeing this from another, I don't know, you're just not in my class, thanks for watching. You can subscribe if you want, but I'm not putting up videos any faster, so have fun. Yay, chemistry.